Yeah. Yeah, so you're going to have to accept some terms, so please feel free to do that. If you're uncomfortable with recordings, well, can also edit you out or something. But well, any more questions? All right, so let's get to it. So what is quantified modal logic and what are we going to study during these 2 weeks? Well, quantified modal logic blends the study of quantified logic and propositional modal logic. So within uh, QML, we can study several number of systems, but we will focus on this system, which is called first order modal logic. First order modal logic is by far the most well understood and studied system of quantified modal logic. And the idea of this is that we get a grasp or an idea of the different ways in which we can study this. Because unlike propositional logic, modal logic, and first order logic, in which we have nice frameworks that have become the standard for how to do this, there is a lack of a single unified system or unified way in which we can do everything. So the idea, ideally, would be that we have a system of propositional logic that we expand to make it modal, and ideally we expand it further to make it first order modal. As we will see tomorrow, that it's not very effective. And what I mean by this is that we are always at the edge with incompleteness results. So for this course, and especially during today and tomorrow, we're going to focus a lot on incompleteness proofs. We're gonna see how we prove it for a propositional logic, for modal logic, and for first order logic. So just to be clear, this is stuff that I hope you have seen for the first time earlier. This is not a good way to see a completeness result for propositional, modal, or first order logic. But as far as I know, you either took this in your bachelor or you took it in MPML. Am I right in assuming this? The people from MPML can confirm that they have seen the completeness theorem for propositional and first order logic. Did someone take MPML at all?
That's correct.
Okay, thank you, Magnus. So now the other side of this is that we have completeness for modal logic. So if you took modal logic with Nick, then you should be golden. So you should understand how the proof works. If not, I'm going to take it slowly with modal logic, but again, this should not be the first time you are seeing this. If it is your first time, however, please let me know at the end if this was understandable and if you have more questions, I will be very happy to answer them. Okay, so now that we are in, with that out of the way, let's talk about first order modal logic, which is normally done with two focuses. The first focus is going to be strictly philosophical, and the other one is going to be strictly mathematical. And the point of either is that we have different goals in mind when we take a philosophical focus or when we take a mathematical focus. If we take a philosophical approach, normally philosophical logicians have some ideas of or intuitions of how generality, existence, and modality work. And what we're trying to do when we postulate a system of quantified modal logic is to find a system that is suitable for our intuitions. However, mathematical logicians, on the other hand, take a mathematical structure and try to show that it's sound and complete with respect to a large class of logical systems. And the more logical systems we find that is sound and complete with respect to, the better. We will, for now, focus our attention in propositional logic, then we're going to mount up to modal logic and then to first order logic, and then to try to see how does it look like when we fit them all together. So we will talk along the road about some other stuff that is not strictly propositional, modal, or first order logic, but I will tell you in time what we're going to do with that. So for instance, when we talk about Williamson, we're going to talk about the higher order logic. When we talk about with Restal, we're going to talk about free logic. And when we talk about, for instance, Shetman, we're going to talk about Kripke-Sheaves, but all in due time. For the moment, do you have any questions? All right. So let's go ahead and let's talk about propositional logic. So what are we going to have in this system that I'm going to present right now? We're going to have variables, propositional variables. We're going to have connectives. I'm going to have, well, some auxiliary symbols, but these are not that important. So variables, what I'm talking about, letters P, Q, R. We're going to work with only two connectives to have a simple system as possible, which are the negation and the conditional. This came out horrible. Let's see if I can make them more clear. There's a tool here for shapes, but I don't know how to use it properly. All right, hope that's clear enough. And then we're going to have the notion of a well-formed formula. So, and for that, we're going to have simply this BNF. It says that uh, every propositional letter is a well-formed formula. The negation of any formula is a well-formed formula. And two well-formed formulas with a conditional in between them, in parentheses, are a well-formed formula. Now, we can call the set of well-formed formulas, we can denote it with this. So it is the formulas of the language of propositional logic. I will try to shape this better when I correct the notes. And well, now we have to present a syntactic system, a derivability system in which we can make inferences with these symbols. And the simplest way to do it is with a axiomatic system that is normally attributed to Jan Łukasiewicz, who was a Polish logician, very important. So we're going to have, as a definition, we're going to have the axioms of propositional logic. What are the axioms of propositional logic? It's what you more or less expect, or I expect that you have seen something like this. So we have this first axiom that's called so weakening. Oh, and here pi, psi, and chi are going to be arbitrary formulas of this set. Then we're going to have the distribution axiom. And we have our third axiom. Ugh, damn. Mhm. Now, this is normally called a Hilbert style calculus. Once we add the single rule of inference. which I will write on this occasion like this. No. You know and love him. It is modus ponens. All right. Then we can very simply derive this relation, define this relation, which is derivability, which it says basically the following thing. So we say that a formula phi is derivable in propositional logic from a set of formulas gamma, it could be possibly empty, if there is a finite sequence of formulas whose every member is one of the following. So it's the first case is that it's a member of gamma, or the second is that it's obtained by modus ponens. Do we have questions so far? All right. With that out of the way, let's talk about semantics. Dependent on your background, you're going to have seen what I'm about to show you in one way or another, but we're going to use a truth functional semantics. I don't know how you were taught this, but I will show you the way I like to do it. And for that, we are simply going to say that we have, as a definition, we have valuation. So what is a valuation? So first we're going to have a set with two elements where 0 denotes false and 1 denotes true. And a valuation or interpretation is going to be a function, small b, that goes from our set of variables to the set we just defined and assigns a value to each propositional variable. We can extend this function recursively so that it covers all expressions of the language, like so. So we're going to say that the valuation of not phi is true if and only if the valuation of phi is 0, and it's 0 if the valuation of phi is 1. And then for the conditional, we use this standard trick, which is basically to say, whoop. So it's, no, sorry, we're going to use the trick. It's 0 if and only if the valuation of phi is true and the valuation of psi is 0, and it is true otherwise. So with this, we can define three very important notions, which are, on the first case, satisfiability, which basically means, so a formula phi is satisfiable if and only if there's a valuation. So there is a valuation such that this valuation makes phi true. That is satisfiable. We're going to say that a formula is valid and we're going to denote it as like this if uh, sorry, I'm confused here. Yeah, yeah. If for all valuations, it is the case that it comes out as true. These are also called tautologies. And lastly, we have the notion of entailment. So the notion of entailment or modeling, for lack of a better word, we first denote it as this, and it basically says that gamma being a set of formulas, possibly empty, but for that we have validities, models or entails phi if and only if for all valuations, if the valuation of gamma is true for all gamma in big gamma, then the valuation of phi is true. Are we clear with this? Are we happy? Because now we're going to go to the meta theorems. All right. So let's talk about soundness and completeness for a second. So these are the most important meta theorems of propositional logic. They're very important, yada, yada, yada. What are we caring about here is completeness. Completeness is normally the harder theorem to prove, and it is basically guaranteeing that our axiomatic system is powerful enough to derive every logical truth. So if you want to, so soundness basically says if something followed like this, then it follows like this, and completeness is the other way around. I was talking this with Andrea the other day, and the way I remember this is that soundness has one S here and two S's here, and if you see the bar here, it's only one, so it corresponds to this S, so to say. And here there are two bars, and here are two S's. I don't know if this helps you. It helps me a ton. So let's go back to completeness. So the idea is to show that there's no thing as an unprovable truth in our system. We have given you a set of axioms, and these axioms are as strong as the semantics that I gave you. So many mathematical structures are complete with respect to propositional logic, and there are many ways of proving it. If you see, for instance, like I don't know if you're familiar with Graham Priest's introduction to non-classical logics. Well, he goes around using the tableau method. Here we will use the notion that we had before, the axiomatic system, and our truth functional semantics. So basically for this, what we're going to use is going to use something called the Hankin method, which I hope that this at least rings a bell to you. Is there someone here who hasn't heard about the Hankin method for propositional logic? Is there someone who hasn't? So you have never heard of Leon Hankin and his method. All right. Great. Great. So basically what we're going to do is we're going to take this and we're going to turn it on its side. So what we are going to prove is that if something cannot derive something, then, so let's put an F here, then it is also the case that it is not able to model it. And for that, we need a very important notion, which is the notion of consistent sets. And then it's buffed causing maximally consistent sets. So the idea of this is that we have the notion of first, so yeah, consistent sets. So the idea is that we have a set of formulas delta, and we say that this formula is consistent if uh, delta doesn't lead to a contradiction. I know that I haven't introduced the falsum symbol in the language. Please bear with me. But the idea of a consistency is it does not contain any contradiction. There is another way of putting this, or to define it in for our language, in a which we say that it is not the case. There is no such psi such that delta derives psi and delta derives not psi. This is how we would put it in our language, but bear with me. The idea of this is that if we know that this is the case, so let's use another symbol for like the meta language conditional. If this is true, then we know that the set of formulas, that it is big gamma and the negation of phi is consistent. Now what we're going to try to do is to expand this set as much as possible to try to see how much we can derive from this set. Oh, by the way, I skipped soundness altogether. But if you have questions about soundness, happy to answer them, but not the focus of the course. But if you're just curious, you should let me know. So the idea is that we're going to define a notion of maximally consistent sets. A maximally consistent set is a set which is consistent, but it is maximally so. And then we're going to have, again, a set of formulas, delta, and we say that it is maximally consistent if, so is MCS F1, no, give me a second. Yeah, yeah. It is consistent, and 2 for any formula psi, if psi is not in delta, I'm writing too fast. Then the union of delta and that formula is inconsistent. So the idea is that we're bridging membership to a set with the idea of being derivable from it. And this is very important for what we're going to do, because now we're going to show that any set can be extended to any consistent set in propositional logic can be expanded to a maximally consistent set. So we start with a couple of things that we know are derivable from this set, and then we expand it to everything that is derivable from this. So the idea of this construction is that basically you're going to the idea of this is that we're going to construct this set. And to construct this set, we need to first know three properties of maximally consistent sets that I'm going to assume that they have, but I'm not going to prove it. So proposition, properties of MCSs. So the first one, it is closed under derivability. So basically says that if delta derives psi, then we know that psi is in delta. Then we have this one follows trivially, but it's very important. So for all psi, either it is in the properties. Let delta be a MCS, or the negation is in delta. And last but not least, very important, it is closed under modus ponens. That means that if psi, then chi, I'll call it chi because it's Spanish, but let me know if you have another name for that. It's in delta. Sorry, no, this is not modus ponens. The idea is that it has all the how it works for the conditional. All right. And now what we're going to do is to try to expand this into a maximally consistent. So with these properties of the MCS and the idea of that we have a consistent set, now we're going to see how are we going to expand it to a maximally consistent subset. And for that, I have better show you this, which I think it's better. So this is called Lindebaum's lemma. And in Lindebaum's lemma, we're going to show how to expand every consistent set to a maximally consistent set. So we're going to call the maximally consistent set delta plus, and we're going to go by stages. What does this mean? It means that we are going to start and analyze each formula that we have. And for this, we assume that the language is countable, which it is, and we are going to enumerate all our well-formed formulas, and we put an index under it to all our formulas, and we define the following sequence of sets. So the idea is that at the beginning, our consistent set that we know is consistent is going to be the formulas that we have. Then we're going to take each one, and then you are going to expand it and add that formula if the set of the previous one, notice here the difference, of the previous one and the new formula, the formula of that stage, is consistent. Then you get another set. If it's not consistent, it means that here in this setting basically means the negation is already there, then you don't add it. And that's it. And then you get the closure of this is, the limit of this is the set delta plus, which is going to be the union of all the sets. And it is routine, but we can talk about it. We can check that it is consistent, and we can check that it's maximal. And basically, it follows that it's maximal because of the construction of how we did it. At every stage we were doing it, we were keeping consistency, and then that means that we kept it under the union of all these sets. And now, oh, okay, no, that was someone getting in. So the idea of this is that now we jump from the maximally consistent sets, and then we try to see how this relates to truth. Because remember that on one hand, we have the derivability relation, and that we have already associated with membership to a set. If something belongs to a set, it can be derived from it. And now we have to tell a similar story with truth. Sorry, and now we have to see how this relates to truth. And for this, the first thing we're going to see is that we are going to make a bridge between the syntax of the language and the semantics that we have provided. So for the first step that we have here is we're going to have something called a canonical valuation, in which we define that something is true with respect to set membership. So if you have a set that contains some formulas, we're going to associate that with truth. But we're going to only do this for the propositional variables. Because otherwise we have to prove it. So first we're going to define the set, and then we're going to prove that this works for the entire language. So we say that we have a valuation and we have a maximally consistent set. And then we say that a letter, propositional letter, is true if and only if P belongs to it. And now we're going to try to show the strongest version of this for the language, which basically means that we expand this bridge not only from the propositional letters, but to every expression of the very formula of the language. So this is, now let's call it a proposition. So we're going to have the truth lemma. And I need a second because I made a typo in the notes and I have to take. Okay, I have to take notes of what I'm screwing up. So, and then we say that, so let phi be a formula of propositional logic. Then we say that for all phi, this is true if and only if it belongs to the maximally consistent subset, maximally consistent set. So to do this, we operate by induction. So is there someone here who is unfamiliar with proofs by induction on the complexity of the formula? Great. So the idea of this is that in case you have never seen this, but you didn't want to share it, the idea of this is that we're going to first take the simplest formula and show that it holds, the thesis holds. And then we're going to show that for arbitrary complex formulas of arbitrary complexity, this also holds using our induction hypothesis. So I have it here. So the proof of this is that we're going to take our variables, and then, by the way we define the canonical valuation, we know that this holds. Our inductive hypothesis is going to say then that if you take any formula, it's going to be true if and only if it belongs to the maximally consistent set of the original set. So we have two inductive steps. Given our language, we had only negation and the conditional, and then let the formula that we are interested. There's a mix with variables. I hope that is understandable, but if you don't, so basically what I'm seeing here is that I formulated this with a psi, and here I'm telling you that it is a phi. Uh, I hope that it is pretty clear. Yes, these are phi's. Sorry, not psi's. Okay, but the idea is the first one is that we let the formula take this form. So we analyze what does it mean for a negation to be true, and then we know by the definition of the negation that we already provided. Remember, we had this very fun definition here. By the definition of it, we know that if the negation is true, then the formula itself must be false. And we have by the induction hypothesis that this is only true if and only if it belongs. So we know that by the induction hypothesis, this must also hold. And then we know from this, by the property of the MCS that I didn't prove, but it's there, is that then the negation, it's in the maximally consistent set. Now, for our inductive step, we need to finish with formulas of this form. And I'm going to only show you the right to left direction. If you want to take the left to right direction, please check the notes. And if you have questions, please don't hesitate to ask me. But the idea is I take the left to right because it's the hardest one, by the way. And what we're going to do is to take the contrapositive. So first of all, yeah, we're going to assume this is what we want to show, but we're going to assume that the conditional is not in the maximally consistent set. So by the maximality, we know that if it's not here, then the negation is. And we know from from a propositional logic, let's say that if the negation of a conditional is true, then the antecedent is true, but the succedent and consequent is false. And since this one is closed on the derivation, we can derive inside the set itself. So we know that this is in the maximum consistent set, and by the induction hypothesis, this checks out, and this one checks out as well. Sorry. And this results in precisely what we want to show, which is that the conditional, it's not. So we show that the conditional, if we assume that the conditional is not in the set, then that formula is not going to be true. So what we have, if we twist it, is that if it is true, sorry, if it is true, then it's going to be in the maximally consistent set. Now we have to show the other way around because the theorem calls for showing it from both sides. It's an if and only if. And well, suppose we also show the left to right direction, which is there, but you can read it in your spare time. And we are almost done here because we know that gamma is in the maximally consistent set, and we know that this is not there. Why? Again, because we started assuming that gamma does not derive phi. We created a set, a consistent set from that. We turned into a maximally consistent set. We checked with the truth, and it says I couldn't find anywhere phi there. So that means that for all gamma in big gamma, if gamma belongs in delta, it is true by the truth lemma, but not psi, not phi is also there, which means that the negation is true, which means that the formula itself is false, which means that this was evaluation that satisfies gamma, but not this, and therefore you get what you asked for. All good? Questions before we move to modal logic? All right. I hope that I haven't shown you anything you haven't seen before. But in any case, let's move on to modal logic. And for modal logic, we're going to keep things more or less the same. We're going to have we're going to have, how do I say this with a, all right, we're going to start from, since you already know modal logic, which is great, we're going to start with the weakest normal modal logic, which is K. Everybody knows it. So, this is the foundation for everything we will discuss later. We will not talk about non-normal modal logics. We will not talk about logics without necessitation. So don't worry. So K is going to have a language as well, which is going to denote here. And we're going to say that K, the language of K, it's basically the language of propositional logic. And we're going to add two symbols. This symbol, which is a box, and this, which is a diamond, which I will try to fill up because sometimes when I write them, I confuse them. But the idea of this it would be that I don't suck at filling this up. All right. The good thing is that we will see a few diamonds. But yeah. So this is the regular diamond. This is the regular thing that you know. The simplest way of doing it actually is without the diamond, and you define it as the dual of the necessity operator, and so on. So I know we're going to do exactly that right now because we're going to have a new set of uh, well-formed formulae, and this is going to so every propositional letter, every negation, every conditional, and now we're going to have every boxed formula. What are we going to add? So axioms. So our axioms are basically the same as with propositional logic, plus the following axiom, which is axiom K. So in the notes, I put the axiom without, how do you say, in bold case? Sorry, no, the system is in bold case, the axiom is in normal script. Here, I don't know how to make the distinction, so I'm going to use colors. So the axiom K is, no, the axioms K is going to be the distribution axiom over the conditional for the box. And we have rules. We have modus ponens and necessitation. And what is the rule of necessitation? It is basically this rule here. This doesn't mean that anything you can put a box to it. Normally, this is if you study modal logic for the first time, they tell you no. This means that if you have a tautology, you can make it into you can have the box next to it. Well, then with this, we redefine the notion of derivability because now we can have as members of the sequence we can also have, let's put, no, this is, yes, this worked. There's a third way in which something can be a member of a derivability sequence or, a proof. And it is the fact that in instances of K, and the fourth way is applications of the rule of necessitation. Let's just call it like this. And now for the semantics. And this is where it becomes very fun because we are going to talk about the relational semantics or Greek semantics. So, since you are very well versed in modal logic, I'm going to skip the explanation of the what is a Kripke frame and what is a Kripke model. It is what you expect it to be. I don't have anything weird here. Uh, if we want to be like very strict, I have something very important in the notes that it is I make a difference between this and this. This one is used when we have local truth. So when it's in a model and a world, and this one is for logical consequence. So let's think. And well, notationally, I only have another thing in my bag of tricks, which is now valuations are going to be functions from the how do you call it? The product of the set of world and the set of variables to be. So that means basically that the first clause in the relational clauses of so this guy is going to be true. It's going to be locally derivable if the valuation of P in W is true. Everything else should follow as you expected. I'm going to make a pause here. Let's make a 5-minute pause, and then I will go completeness. I will go first order logic, and then I will go over the idea of mixing all of what we have talked. So let's reconvene at no, let's give 10 minutes so I can have enough time to make a coffee, if that's okay with you. So we go back at 3:10. In the meantime, if you have questions, please leave them on the chat. I will not be here, I'll be on my kitchen, so please bear with that. But if I come here before 10 and you want to ask questions more generally, please feel free to do that. All right, I'll see you in 10. All right, I'm back. Let me know if you can hear me. Well, you can just react with the things. Okay, Tom, thank you. Um, all right, so we're gonna prove this theorem, but I'm going to skip one of the important lemmata, so that we can move forward to first order logic and discuss and bring the discussion of how to do a system of quantified modal logic, first order modal logic, by the way. So but before that, sorry, let me know, is there questions that we have so far? Are there any questions? Anything? Okay, I just hope that you have seen this for the first time. Not today, so I hope this is nothing new. Maybe some tricks and maybe some change in notation, but otherwise, I hope that everybody is well. Now we will move to prove the completeness, which means that if from big gamma we can prove phi, then from big gamma, sorry, this if this models this, then we can prove this. And we're going to do it again using the Henkin strategy in which we build this maximally consistent set, but we're going to do it a little bit differently because now we have to deal with the formulas that have a box operator. So when we do this, we're going to still do it by the contrapositive, which means that so we say that we prove that if you can prove it, then you cannot derive it. Uh, let's be more clear with this. So the idea is that we do this and then the contrapositive gives us exactly the result we wanted. But the idea now is that we're not going to have a maximally consistent set, but a family of sets, of these sets. So here we're going to build something that is what we're going to call the canonical model. So we construct a canonical model. And how are we gonna distinguish it from other models? So this is the M for model, and then we're going to we're going to put K here to show that this is the canonical model for K. So the canonical model for K is going to be the triple that we already know from our standard models. So we have on the one side, this is a highlighter. We have, oh no, this is not a highlighter. Of course it's not. This is the highlighter. We have a set of worlds. Again, we have that accessibility relationship and we have evaluation. What are these things on the top for? Well, they are going to be a little bit different from the standard model that we have for this. And how are it going to be different? Well, first of all, this is not going to be the set of worlds, but the set of all maximally consistent sets of K. So if you think about it, each possible world in a Kripke model is a consistent set. Since we have equivalent semantics and everything behaves classically, every world that you have in your model is going to be a consistent set. Now imagine that we take the strategy of the maximal consistent set and we do it for every possible world in the model. The idea is that we buff up these sets into maximally consistent sets from the worlds that we have. So W sub no and to the K basically means this. It's the set that you obtain when you have all the maximally consistent sets of K and you start from every world, and you apply the strategy that we talked about earlier. Then you have the initial thing, then you have all the enumeration of formulas, and then you add them in the whether if they are or they are not, depending if they are or not consistent, and then you close it at the top, and then you have it. And then this is going to be defined in the following way. And it is important that that you pay attention here, because I'm going to define it in a way that is different from the Blue Book. I know that you use the Blue Book, but the Blue Book takes the possibility operator as the primitive, and here we're taking the there's a reason for that, but I think that complicates some things. It eases some others. In terms of completeness proof, I think it's easier if we start with the box operator. So what we're going to do here is to define the accessibility relation differently. So we say that for any two consistent sets, delta, sets of formulas in general, delta and sigma, that belong in K. So they are, sorry, I made a mistake. Delta and sigma are maximally consistent sets of K. Then we say that delta accesses in the canonical model sigma if and only if the set of formulas which are necessary in delta belong to sigma. And if you think about it, this is just basically trying to define the accessibility, the condition of the accessibility, the truth condition for the frames, for the K-frame, in terms of the canonical model. Basically saying, I have an accessibility relationship between two sets, maximum consistent sets, if all the necessary formulas, so let's create this. So I have this set, which is delta, and I have this set, which is sigma. And what we're saying with this is if I have then this is the case. So if you find that for all the formulas which are necessary in delta, if they are in sigma, then there is such accessibility relationship. And last but not least, we're going to do define the canonical valuation. And by saying that this is true if and only if P belongs to this. So if we take a look and compare this with our previous completeness proof, this over here is very similar to the canonical valuation that we had. And that's exactly the point. The things that are new are, of course, the canonical set of worlds and the canonical accessibility relationship. But the point is that we keep something from propositional logic. And now we create this bridge between syntax and semantics. And then for that, we need, to prove the completeness, we need two lemmas. I'm going to prove only one with you here, which is the truth lemma. There's another important lemma, which is called the existence lemma. There is a version of it in the notes with my notation, so you can go and check it out. I don't have time here to go over it, but if you have questions, please let me know. So let's suppose, so there's the this is a lemma. So existence, And this is basically proof by, trust me, it's in the notes. And then we're going to show our version of the truth lemma. Our version of the truth lemma now is going to say the following. So we're going to have any formula. So we're going to have a formula phi, and we're going to have a set delta that belongs in our canonical model. And this is going to say that if this can locally derive it, then it's in the set, and we proceed. But here we're not putting the plus on the top because we're assuming that it is in the set in the canonical model, so that means that it's already a maximal consistent set. But so there's not plus on the top of the delta, but it is a maximal consistent set, by the way. So we can piggyback from what we have already done with propositional logic and say, hey, for the atomics and the connectives, so the proof is by induction, and then by propositional logic, we know that atomics are good. We know that connectives are good. And we have our same induction hypothesis. Now we have to show just one case, which is when phi, it is a box formula. So we have to show both ways. We have to show that if this, then this, and if this, then this. So we're going to first show the left to right direction. Oh, no, sorry. This is, I don't know what's happening here. All right, so how do we write it here? This, uh, yes. Okay, let's go with this one, which is then this guy is in delta. So the idea with this is that we proceed by the contrapositive, and this one we can prove directly, and I'm going to show you how. So yeah, so this is wrong. Apologies. This is this. This is that. So we assume that box phi, it's not in delta, and by maximality, we know since it's not, then the negation is, which means that possibly not phi is in delta. And by our existence lemma, there exists a maximally consistent set sigma such that it is accessible from delta and the negation. So basically, what we're doing here is taking a good amount of power from our construction and showing that how does it work? How does possibility and necessity work within the set? And it's like we're doing the logic in the maximally consistent set. And then by the induction hypothesis, since we have that this is not here, then we know that it's not going to be, it's going to be false. So, and if it's false, then we know that it is not the case, box psi. For the other side, we can prove it directly. So just assume that box psi is in delta and let gamma be any world such that set. Oh no, this is a world. Yeah, that's any world such that it is accessible from delta. By the definition of the accessibility relation, it's going to be the case that it belongs there, and by the inductive hypothesis, you get this, and this was arbitrary, so you get it boxed. Great. The conclusion of the proof is that again we assumed this part here, then we took this as a consistent set, we extended it. And then by the truth lemma, we know that all those small gammas that belong there are true, which means that in our case, the negation of phi, since it is in the set, then it's going to be false. And if this is false, this behaves classically, then you cannot derive it. Sorry, you cannot model it. Well. And that's basically about it for the proof of completeness of modal logic. Of course, there are more systems. Here are some of the most famous. We are going to restrict our attention basically to K, because I was for some part of this course is going to be either K or a completely arbitrary system of modal logic. Arbitrary in the sense of like, oh, this works for this, so I'm going to keep it. But it's not like it's random. Basically, we're going to work with something between S4 and S5 or S5 itself. And the idea of this is that, well, you know modal logic, so I'm going to basically skip over this sorry, no, go over this very fast. So the idea is that you can add more axioms to the system. If you add more axioms, you have to correspond the models with a frame property, and this frame property is going to change the way you construct your canonical model. So the idea of this is that you have a series of conditions, and these frame conditions are very interesting, very useful. And then with this, we can show something like more general of how to write completeness proofs for other modal logics. But this is as much as we're going to talk today about completeness of modal logic. So if there's questions at this point, they're very much welcome. Yeah,
Yeah,
Marcus.
maybe it's a stupid question, but where will the lecture notes be made available?
I will send the link to you all today.
Great.
And the idea is that I just hang a file in the cloud or wherever, and then I'll tell you it. The idea is that every day I update them so you can access them.
Thank you.
Yeah, but thank you for that question. All right. So we are not going to go to the fantastic world of first order logic. So the idea is that, of course, you are familiar with with first order logic from some other class that you took during your bachelor or the master's. I'm going to give you my particular flavor, how do I write stuff. But basically, we're going to have a language of first order logic that is going to have the following alphabet. So we're going to have variables that denote objects, variables over objects, we're quantifying over objects, sorry. So the idea is that we have a countable set bar of variable symbols. I will use X, Y, Z, maybe X1. You have a lot of them. You have the predicates, and basically is for each n greater or equal to 0, a set of n array predicate symbols. So that means that we have Pn, Qn, Rn, etc. Maybe not use R because we already used for the accessibility relation. But I mean, yeah, it's okay. And we have quantifiers. And the idea of this is that I'm going to make a trick. I'm going to define the language with the universal quantifier and prove completeness with the existential quantifier. But again, this is just a trick, a standard trick. And the idea is that, yeah, we don't have a lot of trouble with that. Um, I'm not going to add functions or constants for the time being. They are easily added, but the idea is that we add the constants later if we need to, and we will. But the simple point here is that now we have that our set of formulas can either be anatomic, so this should be N. That's our new atoms. Negations are also well-formed formulas. Conditionals also. And whatever we form with a quantifier and a variable to the left. Nothing else is a well-formed formula. What do we have in terms of axioms? Well, we have, in the first place, we have all the axioms of propositional logic. We're going to add two more. So our second axiom to add, sorry, our first axiom to add is this famous universal instantiation axiom. And this has a relatively. Oh, I made the thing disappear. Oh, that's great. I tried like for 5 minutes earlier and I couldn't make it. Oh, this is so great. Uh, is free. Sorry, for x in phi, and we have this is called. Let's let's scratch this and we call it UI universal instantiation, and then we have the axiom of distribution, which says that for all x, if phi that's I, then you have phi, then for all x, psi, but x is not free in phi. I am not going to talk about free and bound variables for now. I hope that is sufficiently clear, or did you took it in one of your logic classes. Um, in terms of rules, we have modus ponens, and then we have the generalization rule. It's basically this one that if you prove something from an arbitrary, uh, yeah, from an arbitrary formula, then you can generalize it. With the quantifier. And now let's talk about semantics, because this is when it becomes really important that we know how our structures are going to work. So in the notes, again, I have another weird M for models of first order logic. Here I'm going to, is a Fraktur M. Here I'm going to just use colors. So we're going to have a domain and an interpretation. So what is D? D is a non-empty set. And I is the interpretation function. that is going to be mapping every predicate to a subset. So it is a subset of D. So the idea is that the interpretation of P, when P is an arbitrary predicate, belongs in a subset of D. So, and then we have, so to make everything work, we need something called variable assignments, in which, so yeah, let's do this slowly. So a definition of variable assignment is the following. So it's a function. So a function G that goes from variables to objects in the domain. This not need be a total function. In fact, the idea is that you have more variables that objects in the domain. I mean, you do you, and then we can denote the assignment of, sorry, with G of X to D, we mean support the assignment that is identical to G except that it maps X to D. Now I'm going to do something again that as we did with modal logic, I'm just going to skip the truth definition, but it has no tricks or not anything special. The quantified formula are still are defined with this G-variant interpretations, sorry, D-variant interpretations. So D-variant assignments. So don't worry, there's nothing new there. What I do want to talk about very briefly, it's about completeness, in which basically it's going to work very similar as we did with propositional logic, but we're going to do something that is special with the existential formulas. So normally you define something that it is, we define not, we need something, sorry again. So in PL, we had the notion of maximally consistent set, but now we're going to talk about Henkin sets or saturated sets, so maximally consistent saturated sets. And the idea of that is that, so let's call this as MCS plus Henkin if for every formula there is an x such that phi, there is a constant C such that if there is an x, then if you replace the constant for the variable, that belongs, this is ambiguous, that belongs to delta. And now what this calls for actually is to define a new language which contains precisely these constants. So we define an extended language by adding countably infinite set of new constant symbols, which we're going to denote like this, uh, to our original language. The idea of this is that now we're going to construct this maximally consistent and Henking sets by the same construction as in propositional logic, but crucially, we're going to now add an extra clause, which is this clause over here. Come on. Okay, if this is what we saw earlier. So if something is inconsistent, then you keep the set as it is. But if it is consistent, you add it. And what means that you add it? In this case, we have to be very careful because if we are talking about an existential, I'm going to block this because I think it's messing up with the pen. If we add an existential, we also have to add a witness for it. That means that if we add that, you add this, then you add this, which is basically what I explained you earlier. But the condition is that C is a fresh constant from C, not appearing in delta at that stage, or it does not appear in psi, in the formula that you're trying to. Now with this, you build the canonical model, and then this canonical structure, you're going to define it as you have your same set of constants, and the interpretation is going to tell you that for any constant, the interpretation of it is itself, and for any predicate, you say that this ordered list belongs to the interpretation if and only if the predication of that belongs to the set. Then you have a truth lemma, which is very similar to what we did. And then for the atomic case, it's going to be something different. But since we have this already, then this follows straightforwardly. The connectivity works as an propositional logic. And then for the quantifiers, here's the trick of how to do it. I'm not going to touch on it. If you're interested, look at it. If you're interested in it, look at it. But the bottom line is that by the same trick, you show that you have a model for the antecedent, and you have and for the negation of the consequent, and this means that you assume that you cannot derive it, and this means that you cannot model it. So, which means that you have completeness. And now, for the last 15 minutes or so, what I want to talk about is the very idea of mixing all of this stuff. So I was using this app. Yeah. So let's talk about the very idea of having a quantified modal logic. So it means that we have the models of first order logic at the main and interpretation, and I raised the hand. And then we have the models of modal logic. And the most intuitive thing that we can do is to say, let's just fusion them together. And then we start from K, then we see what we have, then we go to, more, cooler systems like T, so you have quantified T and so on. The problem with that is that by doing this, you have already infused the system with a lot of assumptions that are not very useful to inferences and ideas that we have when we talk about generality and modality. So syntactically, this is very easy to just put all the axioms and you fuse the alphabets, you create a new version of Wilford formula, you get all your axioms, you get your rules, and then you have something. But then for the semantics, this is when it becomes very hard to do, at least to get something good. So the central difficulty lies in the interpretation of the domain of quantification. So the domains comes from the first order, and in modal logic we don't have that. But in classical first order logic, the domain represents everything that exists. So when you have a domain in first order logic, you are basically quantifying over all of that. There's nothing that you care about that it is outside this. So, but when we move to Kripke framework with multiple worlds, we must ask ourselves, hey, do all worlds share the same domain? So the idea is that this is a very powerful tool that says everything. But this is a very powerful tool to know about truths at other points. So the problem is that we can maybe allow for things, and when we mix them and we have the combination of both, we if we impose, so we are not now going to have a domain of objects. Yeah, this is a list. And this, you might want to say, wait, in this world, I'm going to have Wojciech, Ludovico, and Isabel, but it could have been the case that Ludovico didn't exist in other world, so we just have Wojciech and Isabel. And this is a possible thing. This could happen. This is how we think about modality and possibility in the most intuitive case. This is a actual thing that we can talk about, and derive inferences from. But the point is that we have only one domain. So if we just fix everything together and amalgamate it, we are forced with something called fixed or constant domains. So from a mathematical standpoint, the simplest approach is exactly this one. From a philosophical, this is not the simplest thing you can do, because then you have to defend a philosophical position, a metaphysical position, where everything exists and there is no way it can stop existing, or that new things come into being. So if this is, there's a way of interpreting this, which is like, so people don't die, or, like people are not born, but more or less a metaphysical way of saying this, like things never cease to be. They just change how they are. So the domain can always refer to the same things. There are ways in we can justify this philosophically, but for today, we're not going to talk about that. So basically, this has opened a debate between logicians, mathematicians, philosophers, in which we're going to have various distinct positions that we like or to associate ourselves, or we don't. In the 80s, when this started being a problem, yeah, like a real philosophical problem, we can talk about the history a little bit, but yeah. So the history of quantified modal logic is basically in the 40s. This was formulated in the 60s when the Kripke semantics came. Then the problem started, and then in the 70s and 80s, these philosophical positions came about. The first breach that we have is between actualism and possibilism. So, is someone familiar with either of these positions? All right. So, actualists basically believe that everything that exists is actual. That means that the quantifiers have an existential import. If I say there is an X, that means that there's an X and there's no other way or nothing else needed for that thing to be. So that means that we are not considering anything like mere possibilia. Mere possibilia is some stuff that possibly exists, but there's no actual world, or there's no accessible world. No, sorry, actual world, let's say, but they don't exist in the actual world. They're merely possible. And then, whoop, these people split being, so the verb is, in two. There are things that exist and there are things that just are. And basically, what this makes for is that we split the domain. And we're going to split it into each possible world. So to each possible world, we give a domain, but actualist, what we're going to say, no, we have one domain and we quantify over it. Another related but differently position that has only been started to be discussing in the last 10 years or so is a version of actualism, but it is more stronger than that, I'll say. It's called, mm, so this, come on. This is the debate between necessitism versus contingentism. These four positions are very related and they are here and there, don't worry. But the idea of necessitism is that it is if something whatever is necessarily is something. And contingentism on the other way, I'm going to be very fast because I need the time, but basically, what it is contingent. So there is ways in which things can stop being, and there are things in which things cannot be, and that we basically contrast these two by saying one says that everything that exists necessarily is something. So the idea is that if you go to any possible world, you're going to find what this object is in that possible world. So you can never leave the domain. But the other one is going to split it, and then we're going to say we are going to also open the possibility that there are things in this world, and there are not things in that do not exist in other worlds. The idea was that contingentism is a rebuttal of necessitism. And to see in the last 5 minutes or so, I want to show you how this contrasts by telling you now that we're in the world of quantified modal logic, how three formulas are interpreted according to the different positions. So the first one is going to be for all x, f of x. So the idea of this is that this is important for the actualist and the possibilist debate, in which we want to say that this means, or we reconstruct it as everything is f. But the question, of course, goes, okay, what is everything? So a possibilist or a necessitist is going to say that the quantifier ranges over D, the set of all possible objects. And if we interpret F as existence in space and time, this formula is likely false, but To say that everything exists is to make a claim about the entire logical space, not about just the current world, but the domain itself. However, in the actualist or contingents, for a contingencies, the quantifier is going to range over a particular domain, which is the set of objects that exist in that particular world. So this is going to give us the difference between fixed domain and varying domain semantics. So we have a single domain, and here we have domains indexed by the world. So if you make a choice between either, you're going to want, for instance, if you want a fixed domain, then you're going to be good by just squashing together everything that we've seen so far. If you want a variant domain, if you want to make use of the resources of things that possibly exist, and if you want to make reference to those things and reason about them, you probably need to split the domain within the world. The second formula that it is important is this one. What it basically says is that if every object is necessarily F, then it is necessarily that everything is F. So the metaphysical implication, for instance, is that imagine that F stands for is biological or it's made of flesh and bones. Suppose that in the actual world, the only things that exist are humans. So for every X in the domain of the actual world, it is necessary that it is biological. So that's fine, but now imagine a future accessible possible world where robots come into existence or with the right robots. So we say that there it is not true that everything is biological because robots, of course, aren't. And then the consequence of this is going to be false. So the conflict is going to come that varying domains are going to say, so for varying domains, they're going to say that this is invalid, but for fixed domain, they're going to say that this is pretty much valid and desirable. And then we have the converse of this, but maybe it's not evident from the first look, but you say that if possibly something is F, then there is something which possibly is. And again, this via very similar argument, the varying domain gang is gonna say, I don't want this, but the fixed domain people are going to say, we want this because we don't want our domains to be to be able to add more stuff as we go. So these two formulas are very important in the history of quantified modal logic, and they have names. So this one is called the converse Barkan formula, and this one is called the Barkan formula. The name comes from one of the pioneers in quantified modal logic, which was Ruth Barkan Marcus, a very important figure in the history of 20th century of logic in the 20th second half of the 20th century. And for the most part, we're going to be concerned with with our systems if whether or not they make this valid or invalid. And why are they important? We can start talking about this tomorrow, but basically they are more or less inevitable. But the problem with this is that if you have them, then this puts very strong requirements on how you build your models. And with that being said, I'm going to stop there. I'm going to open the floor for questions if there are any, but otherwise, I think this is everything that I had to tell you today. All right. So I see that there's no questions. So I hope to see you tomorrow. Again, we're going to meet virtually since it's not possible to hold classes on site. I hope you have a great afternoon, and I hope to see you tomorrow.
Thank you, Paulo.
Thank you.